Download this code from codegive.com, link in the description below. OK, let's dive deep into distributed systems, focusing on consensus and the 6-to-1 protocol. This will be a comprehensive tutorial with explanations, code examples, Python based for clarity, and considerations for real-world implementations. Introduction to distributed systems and consensus. What is a distributed system? A distributed system is a collection of independent computers that appear to its users as a single coherent system. These computers can be geographically dispersed, connected via a network, and coordinated to achieve a common goal. Key characteristics of distributed systems. Concurrency. Multiple processes or threads execute simultaneously. Lack of global clock. There is no single, authoritative time source available to all nodes. This makes ordering events challenging. Independent failures. Nodes can fail independently, and the system must be resilient to these failures. Network partitioning. The network connecting the nodes can be partitioned, creating isolated groups of nodes. Heterogeneity. Nodes may have different hardware, software, and network configurations. Why use distributed systems? Scalability. Handle increasing workloads by adding more nodes. High availability. Tolerate failures by replicating data and functionality across multiple nodes. Fault tolerance. Continue operating even when some nodes fail. Geographic distribution. Serve users closer to their location, reducing latency. Cost effectiveness. Potentially lower cost compared to a single, powerful machine. The importance of consensus. In a distributed system, achieving agreement on a single value or state across multiple nodes is critical. This agreement is called consensus. It's essential for data consistency. Ensuring that all replicas of data are consistent. Transaction atomicity. Guaranteeing that a transaction is either fully committed or fully rolled back across all affected nodes. Leader election. Selecting a leader node to coordinate operations. State machine replication. Replicating a state machine across multiple nodes to ensure high availability and fault tolerance. The consensus problem. The consensus problem is notoriously difficult to solve reliably in a distributed system due to the presence of failures and network issues. Consider these challenges. Node failures. A node might crash or become unresponsive. Message loss. Network packets can be lost or corrupted. Network partitioning. Nodes can become isolated from each other. Byzantine faults. Nodes can act maliciously, sending incorrect or conflicting information, much harder to deal with. The FLP impossibility result. The Fisher, Lynch, Patterson, FLP, impossibility result is a fundamental theorem in distributed computing. It states that in an asynchronous distributed system, one with no guarantees about message delivery times, subject to even a single crash fault, it is impossible to deterministically achieve consensus. This means any consensus algorithm must either make probabilistic guarantees, example it will eventually reach consensus. Make assumptions about the timing behavior of the system, example bounded message delays. 2. Introduction to the 6-to-1 consensus algorithm. What is 6-to-1 consensus? The 6-to-1 consensus algorithm is a specific consensus protocol designed to tolerate faults in a distributed system. The 6-to-1 refers to the number of processes involved. It assumes at least 6 processes, nodes, in the system and guarantees consensus if no more than one process is faulty. Asterisk key assumptions of 6 to 1 consensus asterisk. Asterisk at least 6 processes asterisk the system must have at least 6 distinct nodes. Asterisk at most one faulty process asterisk it assumes at most one node can fail or behave maliciously. Asterisk synchronous or eventually synchronous communication asterisk while the original formulation doesn't strictly require synchrony, practical implementations often rely on some form of bounded communication delay or eventual synchrony, meaning that message delivery times eventually become predictable. Asterisk how 6 to 1 consensus works, simplified overview. 1 proposal asterisk each node proposes a value. 2 multi-round communication asterisk nodes exchange proposals with each other. 3 threshold-based decision asterisk each node tracks the number of times each value is proposed. It adopts a value if it has been proposed by a sufficient number of nodes, a threshold. The specific threshold is designed to ensure that even with one faulty node, a majority of honest nodes will converge on the same value. 4 commitment asterisk once a node has adopted a value, it commits to that value. Asterisk why 6 nodes and 1 fault. The choice of 6 nodes and 1 allowable fault is critical to the algorithm's fault tolerance properties. The math ensures that even if one node is faulty, there are still 5 honest nodes. The thresholds in the algorithm are designed so that a majority of these honest nodes will influence the outcome, leading to consensus. If you had fewer nodes or allowed for more faults, the thresholds wouldn't guarantee agreement. 3. Code example, a simplified Python implementation of 6 to 1 consensus. Key improvements and explanations of the code. Asterisk clearer structure asterisk the code is organized into a node class, making it more object-oriented and easier to understand. Asterisk faulty node simulation asterisk the faulty flag allows you to simulate a faulty node. The send_message method includes logic to simulate different types of faulty behavior, sending incorrect values, dropping messages, delaying messages. This is crucial for testing the resilience of the algorithm. The randomness introduced helps to expose different failure scenarios. Asterisk message passing asterisk the send_message and receive_message methods simulate message passing between nodes. A simple message queue is used within each node to store messages before they are processed. Asterisk threshold-based decision asterisk the decide method implements the core logic of the 6 to 1 consensus algorithm. It iterates through the received values and adopts a value if it reaches the required threshold, 4, which is 5 halves. If no value reaches the threshold, it defaults to the initial proposed value, important for termination. Asterisk threading asterisk uses threading to simulate concurrent execution of nodes. This is essential to model the behavior of a real distributed system. Asterisk locking asterisk the threading.lock is used to protect the received_values dictionary from race conditions when multiple threads are accessing it. This ensures data integrity. Asterisk clearer output asterisk prints messages to indicate when nodes propose values, receive messages, and decide on a value. This makes it easier to follow the execution of the algorithm. Asterisk consensus check asterisk after the threads have finished, the code checks if all nodes have agreed on the same value. Asterisk more realistic delays asterisk time.sleep. Calls are used to simulate network latency and processing delays. Random delays add realism. To run this code, 1. Save it as a Python file, example consensus.py. 2. Run it from your terminal, Python consensus.py. Experiment with the code. Asterisk change the faulty _node_id to simulate different nodes failing. Asterisk change the initial values proposed by the nodes. Asterisk increase the number of nodes, you'll need to adjust the threshold in the decide method accordingly, and also the initial values. Asterisk modify the faulty node's behavior to simulate different failure modes. Asterisk remove the time.sleep calls to see how the algorithm behaves in a more synchronous environment. 4. Key considerations for practical 6-to-1 consensus implementations. Asterisk real-world communication asterisk. Asterisk message serialization asterisk use a serialization format, example JSON, protocol buffers, to encode messages before sending them over the network and decode them on the receiving end. Asterisk network protocols asterisk use a reliable network protocol like TCP to ensure message delivery. Consider using UDP if you can tolerate some message loss and need lower latency. Asterisk asynchronous communication asterisk implement asynchronous message passing using libraries like Asyncio in Python or similar frameworks in other languages. This allows nodes to handle multiple messages concurrently. Asterisk fault detection asterisk. Asterisk heartbeats asterisk nodes periodically send heartbeat messages to each other to indicate that they are alive. If a node doesn't receive a heartbeat from another node within a certain time, it can consider that node to be faulty. Asterisk timeouts asterisk use timeouts to detect unresponsive nodes. If a node doesn't respond to a message within a certain time, it can be considered faulty. Asterisk fault recovery asterisk. Asterisk state replication asterisk replicate the state of the system across multiple nodes so that if one node fails, another node can take over. Asterisk checkpointing asterisk periodically save the state of the system to persistent storage, example a disk or a database, so that if all nodes fail, the system can be restored from the checkpoint. Asterisk log-based recovery asterisk maintain a log of all changes to the system state. If a node fails, it can replay the log to recover its state. Asterisk Byzantine fault tolerance asterisk. Asterisk the 6-to-1 consensus algorithm is designed to tolerate crash faults, nodes simply stop working. It is not inherently tolerant of Byzantine faults, where nodes actively behave maliciously. Asterisk for Byzantine fault tolerance, you need more sophisticated algorithms like practical Byzantine fault tolerance, PBFT, or Tendermint. These algorithms typically require a larger number of nodes and more complex communication patterns. Asterisk scalability asterisk. Asterisk 6-to-1 consensus has limitations in terms of scalability. It's suitable for smaller clusters where a single fault is the primary concern. Asterisk for larger, more scalable distributed systems, consider using algorithms like Raft or Paxos, which can tolerate more faults and scale to a larger number of nodes. These algorithms often use leader election and log replication to achieve consensus. Asterisk real-time guarantees asterisk. Asterisk the basic 6-to-1 algorithm does not provide strict real-time guarantees about the maximum time it takes to reach consensus. Asterisk if you need real-time guarantees, you'll need to use specialized real-time consensus algorithms and carefully analyze the timing behavior of your system. Asterisk formal verification asterisk. Asterisk for critical applications, consider formally verifying your consensus implementation using techniques like model checking or theorem proving. This can help you catch subtle bugs that might not be apparent through testing. Comparison with other consensus algorithms. Asterisk Paxos asterisk. Asterisk Paxos is a family of consensus algorithms that are widely used in distributed systems. Asterisk it is more complex than 6-to-1 consensus but can tolerate more faults and scale to a larger number of nodes. Asterisk Paxos requires a leader election mechanism to choose a leader node that coordinates the consensus process. Asterisk Raft asterisk. Asterisk Raft is a consensus algorithm that is designed to be easier to understand and implement than Paxos. Asterisk it also uses leader election and log replication to achieve consensus. Raft is widely used in distributed systems like ECT and console. Practical Byzantine fault tolerance, PBFT. PBFT is a consensus algorithm that is designed to tolerate Byzantine faults. It requires a larger number of nodes than 6-to-1 consensus or Paxos but can guarantee consensus even if some nodes are behaving maliciously. PBFT is used in blockchain technologies and other applications where security is critical. ZAB, Zookeeper Atomic Broadcast. ZAB is a consensus algorithm used by Apache Zookeeper. It's designed for high performance, ordered broadcast of messages in a distributed system. ZAB ensures that all nodes receive the same sequence of messages. 6. Conclusion. The 6-to-1 consensus algorithm provides a relatively simple and understandable way to achieve consensus in a distributed system with a small number of nodes and a limited fault tolerance requirement. While not suitable for all scenarios, it can be a valuable building block for understanding more complex consensus algorithms and distributed systems concepts. Remember that the choice of a specific consensus algorithm depends on the specific requirements of your application, including the number of nodes, the fault tolerance requirements, the performance requirements, and the security requirements. This tutorial provides a strong foundation. To further your knowledge, explore research papers read the original papers on Paxos, Raft, and PBFT to gain a deeper understanding of these algorithms. Open source implementations study the source code of popular distributed systems like ECT, Console, and Zookeeper to see how consensus algorithms are implemented in practice. Distributed systems courses take online courses or attend workshops on distributed systems to learn more about the theory and practice of building distributed applications. Hands-on projects build your own distributed applications using consensus algorithms to gain practical experience.